Thank you for such a generous introduction. I should say this is it gives me great pleasure to be in front of you. Not only I love to talk about the subject I will talk about tonight, but also I would like to thank you who support this wonderful institution. I mean, KITP has had an amazing impact in theoretical physics, in particular, in my area. And all of us are beneficiary of this, so therefore we are beneficiary of your friendship with KITP, and I'm very grateful. As part of this program that I'm here, related to the subject I'm going to talk about, there's going to be a 4-week of activity that we are participating with the top-rate physicists from all over the world, which come together, and we really enjoy the atmosphere and the community that's here, so it really has great impact in development of our subject. Not to mention that I'm from Boston. It's very cold back there, and being here is a fantastic thing at the same time. But anyhow, so I'm going to talk about subject string landscape, the swampland, and how it relates to our universe. So we talk about fundamental forces and the matter. And if you exclude gravity, if you just talk about fundamental forces and the particles they interact with between each other and so on, we have a good understanding of it, including taking into account the fact that they should be described using quantum mechanics. So we can have a nice, complete description of quantum theory mixed with particles and forces. And these are captured by celebrated diagrams here. I'm drawing one of them called Feynman diagrams, which show particles moving around and exchanging mediators of forces like photon and so forth. And we basically understand how this works and how to do these kind of computations to study the probabilities of various things to happen and so forth according to the laws of quantum mechanics. Very well understood, and one of the major achievements, I would say, of last century in theoretical physics is understanding how this structure really works. Very non-trivially, but it does work. But this is excluding gravity. And what happens when you want to include gravity in the mix, which we should, because gravity is part of our universe? So you try to put gravity into the mix, and what that means is that instead of considering a fixed flat space like what we are in, you should allow the space to kind of fluctuate, and like quantum theory. And you might think, okay, a little bit quantum fluctuation here and there should not do much, but somehow everything goes bad. You try to do computations, they don't make any sense. The same formalism, you just put it on this curvy space and let it fluctuate, and it doesn't work. This was already noticed in the, I guess, 1960s, long ago, by Feynman and others who pioneered quantum field theory when they thought about including gravity, and they ran into trouble. So this was a problem. It didn't seem to make sense. So this brings us to the basic conflict that gravity seems to be in conflict, at least naively, it seems to have some problem with quantum theory. Of course, gravity as described in Einstein's theory as a classical description is perfectly fine. It has its own puzzles here and there, but basically it's fine. But when you include quantum things, when you include these quantum fluctuations, then things don't seem to work. But of course, it better work, because we live in the universe which has gravity, and quantum theory is apparently the way things work, so they should somehow work. So that's a puzzle. So how do you resolve this puzzle of including quantum theory and gravity into one mix? And so that's the basic puzzle that was one of the major questions that we didn't know how to resolve until string theory came to the front to try to resolve this paradox or inconsistency. So string theory is a consistent framework which unifies quantum theory and Einstein's theory of gravity, which also includes the matter and the forces and all that. And this is a highly non-trivial accomplishment. And basically, I would say the discovery of string theory, which goes back many decades by now, was in some sense accidental, and we didn't really, it was such an amazing structure that we didn't derive it or something. It just happened by luck to find it. And so what does it do? It basically suggests that we shouldn't think about basic entities in the universe as point particles, but rather as one-dimensional objects, strings. So in other words, the idea is that if you, for example, look at the electron from far away, it might look like a point-like object. But if you zoom in and get closer to it, you'll see some structure, and perhaps it will look like a one-dimensional string extended object. And these extended objects will interact by joining. And so you have, for example, instead of having point particles coming and interacting with each other, you will have strings. As you evolve in time, they can come and join and form. So these two strings can come and join a new string. This process turns out to be describing the fundamental interaction of all strings with each other. So it's a very simple diagram. It's called the pair of pants diagram. It describes, as you can see, if you put it together in time, it's the fundamental entity which tells you how the forces work, basically by this geometry. So it's a very elegant, very simple theory to describe, and seems to resolve the problem of having both gravity as well as other particles in it as some kind of excitations of this vibrating string. And these interactions all give you finite answers, and it's amazing. It's quite remarkable. So, for example, when we talk about protons made of quarks, when we zoom in, we should be thinking of these perhaps as made of entities like strings, perhaps open or closed strings. And we have learned how this can resolve the inconsistencies between quantum theory and gravity. One of the novel features of string theory is the prediction that there are extra dimensions. Now, this is uncalled. We were not thinking about extra dimensions. We have 3 dimensions, spatial and one time. But string theory says, no, I'm not going to work well with those dimensions. You better change your dimension. Now, it turns out that you need, for example, 9 spatial dimensions and 1 time. So what do we do with these extra dimensions? Because we don't see them around us. We only see 3 spatial dimensions. There are no extra 6 spatial dimensions that would have to be there. How do we get these extra dimensions, and how do we resolve the inconsistency between the fact that we don't see them? The idea is simple. The idea is that if you think about dimensions, large dimensions like these sheets, you can certainly roll it up. And you can see that one of the dimensions can become smaller than the other one. So, for example, you can think of it like, you can get this going. You can think of this as a sheet coming together and forming what we call compactifying one of the dimensions to a tiny circle, and you can make this circle to be very tiny and the other one to be long, or perhaps that also longer one could also be compact and can compactify itself. And then you have objects like strings moving around on this space, which look like some objects that, depending on which kind of configuration they have, they describe interesting kind of geometry. So as you can see by this simple picture, having extra dimension gives you a lot of possibilities. What kind of shapes you have, what kind of strings go around where, and so on. So you get an enormous variety of interesting possibilities that you can get from this geometry. So geometry and physics get mixed with each other. So by choosing a geometry, you're basically describing a physics. So for example, we can think about some of these extra directions as being some compact, tiny objects, tiny dimensions like this I'm showing here with this red-looking donut. And the macroscopic space, the 3 spatial dimension, here represented by this blue sheet. And if you think about, for example, a string wrapped around one of the cycles here, for our macroscopic space, it looks like a point particle because it will be over there. On top of this point, you're just wrapping around this cycle. Of course, you can have different particles here based on what kind of strings you include. For example, you could have a string like this. This will look like a different particle to us. Or you could have a string which is vibrating. This will be yet another particle for us. So depending on what kind of things you do, you get different variety of particles and interactions between them, mediated by the interaction, joining and splitting of strings. Now, the kind of things we want to describe our universe, of course, is to lead to 3 large spatial directions and 6 tiny dimensions. So you have to choose such geometries which involve 3 macroscopic directions. And each such choice leads to a distinct observable physics with different particles, different forces, depending on what you choose. Now, of course, you cannot choose everything you want. You have to choose geometries that are consistent with the equation that governs string theory. So you have to do some special geometries which are better and possible to be put there. And they are intricate geometries. They are not that simple to describe. Here it's the artistic rendition of them. So don't necessarily take this that seriously in terms of shape because it's hard to draw a 6-dimensional space. But imagine somehow there's this curved, complicated geometry there, and even though it's complicated, we can describe it very precisely mathematically. So we know what these spaces are, and we know all the nice properties they have, but it's not easy to draw them, that's all. We can visualize it in a different way, but anyhow, this is a kind of artistic rendition. You should think so these yellow lines you see here, you should view them as lines on the macroscopic space, and over each point there's one of these geometries. And in fact, typically we think of these geometries as the same at every point, but you have different choices that you could have picked a priori. So here is the really artistic view of what kind of choices you can have. Of course, this colorfulness is to try to impress upon you that there are many choices. That's all here we are meaning by these pictures. So the physical properties observed in 3+1 dimensions depend on the choice of this space, and the number of forces, the particles, the masses, everything depends on those details. And since there are a vast number of allowed tiny spaces which are allowed, we get a huge number of consistent possible effective theories in 3+1 dimension. This vast possibility is what's called the string landscape, the landscape of the possible physics that we can get. So what is the string landscape? What does it constitute? Does it look like this? Well, what do I mean? Well, we should think about it like this, perhaps, that each choice of this 6-dimensional tiny space you pick leads to a distinct physics. For example, this one leads to this physics over there. This one leads to this physics, that one, and so forth. So there are points that are represented by these points on this landscape, which are obtained by choosing different kind of 6-dimensional compact spaces. So this is what we mean by string landscape, the possibilities of what choices we can have. Our universe is just one of them right there. Hopefully one of them. So which one? Well, one of them, the one we are in. Now, going from the choices of what this intricate mathematical space is to the landscape, to these possibilities, is too cumbersome because there are a huge number of possible ones. And so this raises the question, can we just reverse this and just pick a consistent looking theory in 3+1 dimensions and not worry which compactification, where do we get it from? Because there's so many choices, you pick what you'd like. It's just like going to a store, I like this, 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 this. Please find what space will give me this, please. I don't want to worry about it. Can we do that? Can we just order a physics? I want this kind of particles with this masses and so forth, with these charges. If that's possible, then we don't have to worry about this complicated 6-dimensional space. Some string theorists will worry about it, but we just order our particles of what we want. Can any imaginable universe with a prescribed set of particles and forces occur as a point in the string landscape? Can we have very heavy electrons, for example, instead of the light ones we have? Can we have a universe with no matter at all? Can every matter structure occur in some universe, not ours, in some other universe? Could it have existed? Could it exist? The answer, from what we have learned in string theory, seems to be no. In fact, exactly the opposite seems to be true. Almost no matter you order is allowed. So if you choose a random set of particles and forces, it's almost guaranteed not to exist in the sense that it cannot be consistently described in the context of mixing with gravity in a consistent way. What we are made of, matter and the particles and the forces we are made of, seems to be jewels, very rare jewels. Even though there are a huge number of them, still a rare jewels compared to the vast possibility of all possible physics you can think of. So in some sense, we are in a very, very special situation, and we would like to then understand what constitutes this jewel. How do we describe the interesting subset that constitutes allowed universes, which we are one of it? What are these special features? So the ones that are not good we call the swampland, because they looked okay, just almost like landscape, but if you dig deeper, it's no good. Okay? So essentially, all the quantum systems of matter that you might think of belongs to the swampland. there are only a very small subset, like these islands or these little things, which belong to the string landscape. And we would like to understand what are these points which are coming from these interesting choices that we can have. So these are very special. What we are made of or what kind of forces are allowed are very special. So if you think about, this is a picture of it in terms of a space of possibilities of consistent, possibly consistent particles and forces, which essentially all of them belong to the swampland, except a few of these, which we believe in some sense they are finite number, actually. You can count them. So we believe they are finite. They could be a huge finite number, but we believe they are finite. And they constitute part of a string landscape. And one of it, what we call here standard model, is what we are made of. The forces, the matter, the electrons, the quarks that we know and love, is one of those. So then the question naturally arises, what distinguishes the landscape from the swampland? What additional consistency conditions are necessary in a quantum theory of gravity which are absent when we remove gravity? What does gravity tell us? What does gravity like? What does it not like? Can we delineate these conditions? We do not know them all. I wish I could tell you if you have A, B, C, D, etc., you're done. We don't know it. So the Swampland program, part of what we are trying to do in this workshop to better understand these criteria, what are these criteria which allow a theory to be good and which ones are not good? So try to find these criteria. So we are trying to make progress about what are the requirements for this thing to be good. So I can tell you what we have learned up to now, some aspects of what we have learned up to now. So as I said, not all consistent-looking theories arise from string theory. Some of these observations can be captured by some principles, and some of them can be motivated by ideas related to black hole physics. Somehow understanding deep aspects of black holes, which are one of these mysterious objects that Einstein's theory of relativity predicts, turns out understanding quantum aspects of these objects leads to some of these conditions, and it seems to explain some of these mysteries. So these kind of ideas turn out to lead to some specific predictions which can have concrete consequences for cosmology and particle phenomenology of our universe. So it's very interesting to try to see how these general conditions tell us about what we know about our universe. So here I will present some of them and explain their motivation and the consequences for observation. So before doing that, I need to review some basic facts about black holes. So, well, for a black hole, if you fix a charge, electric charge, let's say Q, and you fix the total mass m, then it turns out that for this given mass and given charge, as long as the mass is bigger than or equal to the charge, there is a black hole. Namely, you can write a solution to Einstein's equation, which when you measure its mass and its charge have this relation, it's nice, spherical symmetric, and so forth. And the extremal case is the case where m is actually equal to charge. So the mass is usually bigger than charge, but there's an extremal case called the extremal black hole, which just saturates this inequality, m equals to q. Black holes have an event horizon. So there's an area where if you get closer to it, then you fall in and you cannot get out. So this is called the event horizon of the black hole. And moreover, as Bekenstein and Hawking showed us, black holes have thermodynamical properties. In particular, they carry entropy. So the entropy of a black hole means it's the degrees of freedom it's made of. Despite the fact that Einstein's equation suggests there's a unique solution, quantum aspects reveal that no, there must be more to it. There are more microscopic degrees of freedom. The entropy of a black hole is related to the area of this horizon divided by 4 in some fundamental units. So it turns out, therefore, if you have a big black hole, it will have a huge entropy based on the fact that it has a big area on fundamental units of physics. So the number of states of a black hole is exponential of the area of the event horizon, the area of the sphere, divided by 4. It's a nice simple formula. And the other fact about black holes is that black holes disappear by gradually emitting elementary particles. This is what's called the Hawking radiation. So even though we originally thought nothing can get out of the black holes, Hawking showed that indeed that's not true if you take into account quantum effects. And black holes gradually lose their mass by emitting radiation, the Hawking radiation, and after a while completely disappear. So the black holes are gone after a while. Sometimes you have to wait a long time, but they will be gone. And there will be no imprint left. They're just gone. So, okay, so that was some preliminary about the black holes, and I'm going to say how some of that will fit in some of what I'm going to tell you. So these are some of the requirements for having a good landscape. In other words, what constitutes a good theory? A good theory which wants to couple to gravity has no global symmetries. Now, what is global symmetry? Well, global symmetry in the jargon physicists use is basically something that if you count something, you don't lose it. Like if you have 5 things of something in a bag, if you measure tomorrow it's still 5, the day after tomorrow it's still 5, you don't lose it. It's conserved, conservation law. So that's what I mean by global symmetry. Global symmetries are one of the bread and butters of quantum field theories. We love symmetries as physicists. It says here the surprising statement that if you have global symmetries, gravity doesn't work. Gravity does not like global symmetries. Very surprising. We would naively have thought that symmetries are good, a good thing to do. And gravity says, no, I don't like symmetries. Somehow, gravity is not good with symmetries. No global symmetries. For gauge forces, like, for example, Maxwell field and so forth, you could have charges that are conserved, like electric charge. So when I say charges here, I'm distinguishing what we call global symmetries versus gauge symmetries. Global symmetries are things that you just count which don't have any electrical field emitting from them. And then there are things like electrons where they emit electrical field outside. That's what we call gauge charges and so forth. So we distinguish these two cases. We can have symmetries related to electrons, but not to things which have no electrical field coming out. So if you have something like electrical fields, it turns out that you get all possible charges. So in other words, you will get every charge that you can conceivably imagine must be in your theory. You should be able to create these particles of arbitrary charge in that theory. A good theory in the landscape has the range of the fields should be finite. So in the context of field theory, we talk about fields, and fields typically have infinite range. But in the context of quantum gravity, the fields are kind of truncated. So this is a very strange feature of why. The theory must admit higher dimensional objects like strings and membranes. So this is actually, I will explain how this principle that string theory suggests there are strings actually also can also be working well with other things other than strings, like membranes. But it cannot do without them. In other words, there must be some extended objects in the theory. You cannot have a good theory of gravity without having extended objects. The fifth thing is that gravity is always the weakest force. So we have electric force, and we have strong forces, and the weak forces in our universe. Gravity turns out to be the weakest force among the forces we know. Here, we are saying that no matter which universe you pick, it better be the case that the gravity is weaker than the other forces. So it's not just an idiosyncrasy of our universe. It's a property of any consistent theory, even though we could have contemplated a universe for which the gravity was among the stronger forces. That theory would not be consistent. So somehow the fact that gravity is weak is a necessary condition for the quantum theory of gravity to make sense. And then I will describe the consequences for cosmology and the dark energy and the fate of our universe. Okay, so criteria number 1, no global symmetries. There are no global symmetries allowed. You cannot count things and hope to have the same things forever. So suppose you have a bag of something and you say there are 5 of them there, and somehow tomorrow it might be gone, and not that you can say, oh, somebody took it. there's nowhere in the whole universe. They're gone totally. They're just, there's no print, there's no way to be found, and therefore you have lost them. In other words, it's not conserved. How does that happen? Actually, the idea is very simple. It's basically related to black holes. You see, suppose somebody said, I have this bag of this, let's say, 5 of these guys here, and then there's a black hole over there. I'll throw this into the black hole. You say, okay, you threw it in the black hole, that's fine. But black hole, outside the black hole, you'd have no imprint of what is inside other than its mass and charge. So you wouldn't know what you have thrown other than the total mass and the charge. And so you say, okay, no problem. I can go in and get it and see what's there. But after a while, I told you that the black hole evaporates. So you have this charge, you have thrown it into the black hole, it's gone inside, and after a while, the black hole evaporates, and it's gone. You lost the charge with the black hole. That's it. Global symmetries are not allowed because black holes can gobble them and make them disappear. So this simple phenomena of the black hole physics tells you there's no conserved quantity, and that's in fact the fact we have seen in string theory, consistent with what we know in string theory. Now, suppose you have what we call the U1 gate symmetry, which is what we also can think about the Maxwell field, the electric field and magnetic field we are familiar with. Suppose we have one of those. The claim is that you can get all the charges that are possible do appear in your theory. Like electron has the basic unit of -1 unit of basic charge. Proton has a +1 unit of that. All of these appear. In other words, it couldn't have been that you have twice, electron would have twice the basic charge and the first elementary charge doesn't appear. That cannot be. That theory would be inconsistent. You should have the basic ingredient with the basic charge should be part of your theory. Otherwise, the theory would not be consistent with gravity. Now, how do we see that? Why does gravity require that? Because we could easily imagine a perfectly consistent theory without gravity for which we didn't have all the charges. That would be perfectly fine. For example, Maxwell theory itself, with no charge at all, is a perfectly fine quantum theory. In fact, it's one among the simplest ones. But with gravity, somehow that doesn't work. Why doesn't it work? Again, black holes. Pick a charge that you like, Q, and consider a black hole with that charge. Bekenstein-Hawking entropy tells you that there are states with that charge in your theory because there is a black hole with that mass and charge. And so, therefore, you cannot say that that charge is not part of your theory because black hole is part of Einstein's theory. Therefore, according to Bekenstein and Hawking formula, this implies that you have charged states. You cannot avoid them. So you see that some of these principles we can understand relatively simply by connecting it to basic aspects of black hole. But this is not true about all of these criteria for the Swampland. We do not know, we have discovered criteria which we do not have a deep understanding why they are true. So how do we observe it? Well, we look at all the possible ways we can put these consistent theories in string theory, and we see a pattern. And then we say what these patterns seem to imply. So I'm going to tell you some of these patterns where we do not have a derivation as simple as I just told you about it in the context of black hole. So we can gain more and more reason for why they are true by trying to check them with more examples or try to find consistency examples based on similar things to black holes. So one example is that the range of the fields is finite. So in the context of quantum theory, you talk about like electric fields. So you can also have things which are not a vector but functions, like what we call here phi. Typically, they take values, arbitrary values, any number you want from -infinity to +infinity, and there's no problem. And that's what we deal with in the context of quantum theory, and there's no issue at all. In the case of gravity, it turns out the range gets truncated, that you cannot have an infinite range for that field. Somehow the range is truncated by a basic unit in physics, which is what's called the Planck mass. So there's a finite range in these fields. More precisely, what happens is that you can go farther than that range, outside that range. But what happens if you go outside that range? You get a tower of light state coming down and destroying your simple description of physics, the one you thought you had. So you have to modify your description because you get all this tower of states coming down and exponentially losing their mass, the farther away you go in this field space. So we have this amazing picture where we have the space of these fields, which when you go very far away, you get, as you go to these corner regions, you get tower of light states coming down. This is a bizarre feature from the viewpoint of quantum field theory. There's no reason why it should have happened. But this always happened in all the examples we have studied in string theory. Why? What does this mean? Why is this important? It turns out what this means is that as you go from one place to another, when you're going toward these corner regimes, the far away distances in spaces, in field spaces, what you find in new physics description takes over. Your description changes completely, and that is what we call duality. You go from one picture of physics to another picture of physics. So we say this is what is the dualities, which means that you have a reshuffled degrees of freedom of one kind of physics with another one. So you get two different descriptions of the same system in these different corners, which look very different, but superficially very different, but actually identical. And so this is somewhat like this drawing. I like this drawing of Escher. It really displays this feature of duality very nicely. So you see there are different corners here, like these, just similar to the different corners I was talking about here, where different things are going on. You see there are these birds, the black birds here, the white birds here, there's field, there's night, there's sky, and so forth. They look very different. So each corner has a story to tell. But actually they fit together into one complete theory. They morph very nicely, and it's one picture, one complete picture. And this turns out to be a generic feature of what happens in physics, in the context of string theory, that there are all these corners that they look very different, but actually, you know, this white bird here becomes that white sky over there and so forth. So they are kind of dual to each other. They transform their roles, but nevertheless they fit beautifully, just like this drawing. So this is one of the lessons we have learned in string theory, that quantum theory of gravity likes dualities, that if you try to make the theory more and more difficult by going to extreme corners, it becomes simple. Just like this drawing. You see, if you want to go to extreme to the left, then it's a simple story. To extreme to the right, another simple story. In the middle, it looks a little messy. So somehow extremes are easy, despite what you might have thought. That seems to be the case in this drawing. It's also the case in string theory when we study this. So the extreme limits are simple. You might think that you can make something extremely more complicated. No, there's a maximum complexity. It becomes simpler after a while. Why is it like this? We don't have a deep understanding. This is just what we have discovered in the past 20, 30 years. We know it's true, but we still don't have a good reason why it had to be so. The other thing is that string theory demands extended objects. Of course, when I say string theory, you might say, well, I started with that assumption. But actually, it turns out that what we today mean by string theory is a broader concept than just a theory of strings. In fact, we have learned that you could sometimes have membranes replacing strings. And the question would be, could you have had none of them at all and somehow related to strings? And it turns out that that's not possible. You always need some extended object. And why is that? Well, it turns out that the simplest description is like this. You take your space, and you imagine rolling one of the dimensions, just like I showed you in that piece of paper where you rolled it. Imagine you roll that to a circle of some radius. And suppose you squeeze that radius down, or you squeeze or make it big. So you can write the radius as exponential of what I call that field phi. If you take the radius to be huge, like that huge cylinder I was talking about, it corresponds to going to one of these extreme corners I was showing you in the drawing. And in these extreme corners, you can have light waves going around the circumference of the universe, and these correspond to light particles from the viewpoint of one lower dimensional theory. So that's a manifestation of what I was telling you about the tower of states. In this case, the tower of states are these light waves, ripples you can have on this big space. But if you take and make the space instead smaller and smaller and smaller, you might think that these ripples to create these ripples is harder and harder, so therefore it requires a huge energy, and therefore there is no light tower I was talking about. Unless there are things which are extended like strings, because if you have strings, you can wrap around the circle, and if you make the circle smaller and smaller, they get lighter and lighter. So to get this light tower, we need extended objects. So that is an actual statement that this principle, that going to extreme corners you get light states, predicts that you need extended object in your theory. Now, the next thing, gravity is the weakest force. So what does this mean? So suppose you take a charged particle with charge E. As you know, there's a gravitational attraction between any two massive objects, whose gravitational attraction goes like square of mass. If you have the same object, it goes like a square of a mass divided by the distance squared. This is Newton's law of gravitation. I've chosen units so that the Newton's constant is 1. There's also the electric repulsion. If these have the same electric charge E, they will have a repulsion proportional to the square of the electric charge divided by distance squared. Now, you might ask, which one wins? Does the gravity win? Does the gravitational attraction win, or the electric repulsion? So gravity is always attractive, and electric force of the same object with itself is always repulsive. So which one wins? Well, here I want to argue that the gravity always loses. Gravity is weaker. Mass is always less than the charge. So gravity is always the weakest force. Like electron is, if you have two electrons, the gravity force is negligible compared to the electric repulsion the pair of electrons feel from one another. Why is it like that? Why should it be like that? Could it have been differently? Could it have been that, no, the gravity is stronger than the electrons bind, for example, or they are pushed together? The answer is no, they couldn't. And again, black hole explains it. So how does black hole know about what we call the weak gravity conjecture? The idea is that you start with an extremal black hole. Extremal black hole, remember that the basic mass and charge relation of a black hole is that the mass is bigger than or equal to its charge. So the extremal case is mass equals to charge. But I also told you that black holes evaporate. They disappear. So how could this black hole disappear? Well, it has to emit elementary particles of mass and charge. So it undergoes what we call the Hawking radiation. So you emit a little bit of a charge and a little bit of a mass. So therefore, the charge goes down and the mass goes down by conservation of the charge and the mass. But the remaining black hole should satisfy the restriction that the net mass is bigger than the net charge. So m minus small m should be bigger than q minus small q. On the other hand, we knew that we started with q equals to m. Therefore, it means that the mass that you emitted should be less than its charge. So for this to be able to emit and go away, the mass should be less than its charge. So this is related to the fact that we expect black holes to evaporate. You can extend these ideas of weak gravity conjectures not just between point particles, but also between sheets and so forth, that always the attractive force loses compared to the repulsion that the charged objects experience. So this seems to be a principle of quantum gravity. So perhaps the most exciting or most interesting possible application of these ideas of Swampland is to cosmology. What do we know about the macroscopic structure of our universe? Does it tell us about that? Can we learn anything about the cosmological questions from the Swampland? So we have this picture about how the universe came to be by a Big Bang. The initial time we don't quite know. At the very beginning, maybe inflation, maybe something else. We don't exactly know, but we know after a while the Big Bang takes over, and we have beautiful description of the theory, and everything fits beautifully. And the time here is evolving to the right. So the universe expands and so forth and cools. And the question, of course, is, will it end? What will happen? We all would love to know that. Well, we'll have something to say a bit, hopefully. We'll see. But string theory landscape tells you something. The only universes that we know that last forever have a special property called supersymmetry. So do we have supersymmetry in our universe? All the other universes which don't have this property disappear after a while. Okay, well, let's search what is the supersymmetry. Well, the supersymmetry tells you that for every particle of a mass, there's a shadow particle, another particle of exactly the same mass, but their spin is different. Their internal spin is different by half a unit of Planck. So, for example, one of them is a boson, the other one would be a fermion. If this is fermion, the other one would be a boson because they differ by half a unit of spin. Supersymmetry means that, in particular, the spectrum or the masses of the particles come in pairs. The particles come in pair. Okay? For a supersymmetric case, we have learned quite a bit about compactifications of string theory. And we know there are only two allowed types of solutions that you can end up having a possibility in a macroscopic leftover space. One is what we call Minkowski space, which means our universe, flat space, what we usually call flat space, with zero energy, what we call cosmological constant vanishes. The energy is the same as what's sometimes called cosmological constant. And another thing that we know as a consistent solution with supersymmetry is anti-de Sitter space, ADS, with negative energy. So there's energy pervading the whole universe. It could be zero or negative for these supersymmetric ones. And many of them are absolutely stable. And no supersymmetric theory allows positive energy, what we call de Sitter space. So positive energy is not good with supersymmetry. Supersymmetry doesn't like positive energy, it likes negative energy. I don't know why, but it's just negative. What can I say? So no stable solution known without supersymmetry. Unfortunately, in our universe, we have not observed the partners, I'm sorry to tell you. So according to what we know in string theory today, our universe will not last forever. We have no example in string theory when we don't have supersymmetry that the system is stable forever. It always will undergo some decay, disappears. How much time do we have? No, I'm just hopefully we'll be around for a while. But anyhow, the theory predicts that we are going to disappear. Okay? Sorry, this is a bad prediction, but what can I say? So we will not last forever. So how long do we have? Well, we are here. Here I'm drawing the years, 10 almost, that's around 14 billion years. We are here. And let's populate it with some numbers here. Well, there are not too many numbers, but one particularly interesting number is when protons decay, for example. That's 10 to the 35 years, long time from now. So maybe that says, okay, don't worry, you have a long way to go before at least the protons decay, so at least nothing to worry too much. Okay, good. Okay, so that sounds good. Now, on the other hand, it was observed not long ago, in the 2000s, near the beginning of the century, that there is positive energy, dark energy, in the universe. The energy that pervades everywhere is positive. Actually, this kind of goes hand in hand with what I said. We don't have supersymmetry, so I said supersymmetry likes -1 or 0, and our universe is positive. That's another manifestation that we are not in supersymmetric case. So the whole universe has positive energy, but it turns out there's a natural time scale associated with positive energy. In other words, you measure the energy here, and then something says, okay, there's a time associated with it. That time, you might be saying, what is that time? Is that related somehow, maybe, no, to the age of a universe or lifetime of a universe? Could that time be special? Let's see what it is. That time turns out to be 10 to the 11. Oh, boy. It's too close. Okay, so what does this mean? So we measure the dark energy, and it's very close to the age of our current universe. Well, this is called the coincidence problem. So you measure the dark energy, this basic quantity, which has a natural time associated with it, and the time turns out to be very close to the age of our current universe. Is that an accident? Is this a coincidence? It's called the coincidence problem, so that already tells you some verdict. It's a coincidence. Well, let's see. So let's go back and dig a little deeper. Can we say something about these? So we want to have positive energy. Our universe has positive energy. That's what we call de Sitter space. How do you get positive energy? Well, the way you get positive energy is that if you have, for example, a potential for some field, you can have a minimum at a positive value. That's all. And it turns out that the value for that energy is very tiny, about 10 to the minus 122 in fundamental units of physics, which is why originally most people bet it's exactly 0, incorrectly. It was discovered. So it's a tiny number in fundamental units, but it's there, it's positive, it's measured, so we know it's true. And so this could be our universe. We could be stuck here at the minimum of this potential with this positive energy. And that's the current picture, popular picture of where we are in our universe. It's called the de Sitter space. But you might ask, why not the rolling scalar potential? Why not something like this? But there's a strange feature. So this kind of model is what's called the quintessence model, the models in which you have a rolling scalar field instead of being stuck at the bottom. There's a strange feature of them. Because we have measured things are not changing too much, like the energy of the universe doesn't seem to be changing too much. So if it's rolling, you might say, wait a second, we know it's not supposed to be changing, so why is it changing? So you put a bound about how fast it could be changing, so you cannot be too steep a potential. You find not only the potential is 10 to the minus 122, but actually the slope of the potential is also less than 10 to the minus 122. You say, come on, there are too many small numbers here. Why is the slope so small? Why is the value so small? You're willing to perhaps accept one coincidence, but why the second one? Well, it turns out that the bound you need for it to work is related actually to the value of v. So the slope somehow is of the same order as v itself. And it turns out that in examples that we see in string theory, this typically is the case. That is, the slope and the value of the potential are correlated. So this fine-tuning that from one viewpoint looks like an amazing fine-tuning is only one fine-tuning, not two. So the slope and the value somehow get correlated. And this is one of the things that we have been discovering in the context of the examples of landscape, that landscape seems to have potentials which are rolling with a steeper slope. Now, string theorists have attempted to construct de Sitter vacua, the ones which I showed you in the minimum, and we're still not sure if we have a reliable example of that type. They could exist, they may not exist, but the techniques to construct them are very hard, and we don't still have a consensus whether we can have a minimum of this potential or not. So we are still not sure. But what do we know? Well, we have two possibilities, either this or that. This one is currently more popular than this one, but let's consider both possibilities for now. In either case, it's not going to stay there. You see, in this case, we know always there is a case that the potential comes down beneath where it started with. And so what could happen is what we call tunneling. So we can tunnel out of our universe to somewhere else. So our universe will disappear by tunneling. So if we are in this kind of a universe, what will happen is that this tunneling means that you end up over here, at least some point in the universe ends up there, and that is like a bubble and starts expanding and taking over the whole universe. The whole universe will be taken over. So we will not be around to be worried too much because this bubble moves with the speed of light. It takes over so quickly we won't notice too much. So that's one possible answer. But the other one is a bit more gentle. It just gradually rolls. Gradually rolls, but what happens is that if you roll a while, what's going to happen is that you get light particles. Because as I mentioned, if you move a lot in this field space, you get a tower of light particles, which means the particles we are made of become too heavy compared to these new entities. And so we would be like the dinosaurs, which will decay to these light things. So we will disappear because we go to the light ones. And so there will be a phase transition if we were in this situation. So then the question will become, how long will either of these take? So we cannot be sure about them, but there are reasons there are estimates about how long this will take and how this decay will last, related to some of the observation of Swampland. And they seem to suggest in the alternative A that the time it takes for you to get these light states is 10 to 50 times the current age of the universe. And in the other case, in the other alternative, when you have a minimum, 100 to 200 times the current age of the universe. These are not firm numbers, and we are still trying to debate to what extent they are true, but these are ballpark numbers that are getting from these ideas, from this study of these Swampland ideas. Surprisingly or not, this is actually corresponds to that time scale of the dark energy. So then it would not be a coincidence, namely, whenever you are in a universe where you measure the dark energy, you're actually about to disappear. So in other words, a typical energy in the universe will be related to its lifetime. So it's not an accident anymore. So this is not a coincidence, it seems, that, I'm sorry to say, that the dark energy predicts not too far in the future, the universe may disappear. So with that, let me conclude that Swampland ideas are beginning to be sharpened, extended, and better understood. They define some universal properties of consistent quantum gravitational theories, and they could have dramatic implications about our universe. Thank you.
I'm sure we have questions before the universe ends. Yeah, you want this? I'll give you this.
Two questions, if I may. About halfway through, you had a list of 3 items. Do you remember that?
If you mention, I can.
Oh, that's okay. The first one was not all consistent theories arise from string theory. I think that's what you said.
Yes. Not all consistent looking theories.
Consistent looking theories.
In other words, you could imagine that it naively looks consistent, but they are not consistent.
Oh, okay. Well, that's all right.
Let's see.
No, that's before that. That's it.
Yes.
It's looking theories. What does that mean?
Yeah. So what that means, as Dave is saying, is that if you ignore gravity, they are consistent.
Oh, okay.
If you just delete gravity from the mix, they're fine. But with gravity, we don't know, and they're consistent looking. That means consistent without gravity.
Okay. The second question was, thank you, was if we ignore the Bekenstein-Hawking hypothesis, isn't charge conserved globally in that case?
So again, I distinguish 2 types of charges. One is what we call electric charges, where there's electrical field emanating, and the other one where there is no electrical field emanating. If electrical field emanates from the charge like electron, they don't disappear. Why don't they disappear? So what happens to those? So if you throw an electron inside the black hole, and I say black hole disappears, well, as it's emitting, since electrical field comes out, it emits more the electric negative charge than the other ones. So therefore, they will get out. So you will not lose the electric charge. Whereas if you did not have electrical field coming out, the things that come out of the black hole are neutral with respect to that. It doesn't distinguish them. So that's why you lose it in that case, but not in the other case.
While you've got that slide up, could I ask, back there, when you were explaining that, you used the term motive and motivated. What exactly do you have in mind?
Yes, motivated means that, so some of these pictures that I showed you, like the black hole evaporation, gives you an explanation. By motivated, I mean explanation. They are not what I would call a rigorous mathematical derivation. That's why I wouldn't say this derives. So it kind of explains it, but it's not at the rigorous level as we would say it's a math theorem. So I wouldn't say that, but kind of explains it. That's what I mean. So it's not as satisfactory as I mean, we would like to have even a deeper understanding of these principles.
You have the equations between M and Q and the
Yes.
inequality.
Yes.
So a question of units or what?
Yes, good question. Good question. So I was measuring everything in fundamental units of physics. So when I said M, it means M in Planck units. So M over M Planck. And the electrical charge, like the fine structure constant, what we call is dimensionless. So you could compare M over M Planck to the charge.
Well, you keep mentioning about things escaping from the black holes, but things can't escape from the black holes without going faster than the speed of light, can they? So, I mean, are the particles escaping going past the escape velocity?
No. So particles go in, but what happens, so the Hawking discovered this amazing phenomenon of evaporation. The way it works is the particle that goes in is gone. So what happens is that near the horizon, there are these little fluctuations where occasionally a pair of particle, anti-pair particle get created at the horizon. one of them falls in, the other one goes out. And that the one that goes out is the radiation. That's what happens. So that's a quantum fluctuation of the horizon.
Oh, yeah. Yes, it's a very inspiration talk. And I have a question regarding to the first criteria. Because we introduce gravity, we break the symmetry. And the example for that is the black hole Hawking radiation, the black hole dissipated. And it reminds me, like, in quantum mechanics, it's also very hard to incorporate frictions, which is also like a dissipated force. And in classical mechanics, it's easy to include friction. So do you think this, like, including friction to quantum mechanics, like is this also like kind of a good analogy to?
Yeah, you're asking
consider?
a very good question. So let me explain. So the friction usually in classical mechanics, you lose energy, you go somewhere else.
Yeah.
This never happens in gravity. And that's one of the amazing things that people were confused about and still are debating, but we think we know the answer, that you don't lose things from the evaporation of black hole. More precisely, the information, what's called the information puzzle, which is an analog of your friction that you could have, lost somewhere to something that we cannot measure. So information is not lost. The black hole evaporates in what we call a unitary way, which means all the information can be recovered from it.
Yeah.
That's all. So there's nothing lost, even though it appears that there's something lost. And that's one of the amazing. The black hole has this bizarre feature that it makes things disappear, but in a way you can recover it in some ways.
So it's like
it's a funny thing.
Yeah, it's very interesting. So in the black hole, so in classical, you dissipate energy into other environment, but in the universe, you don't have an environment. You only have the universe itself. So it's
So for example, the energy of the black hole goes to the radiation outside the environment. So indeed, radiation is the conservation of energy, requires that energy goes outside, and it does go outside. So it's not where the black hole used to be, but it's given to the environment.
Okay, thank you.
So, Cumrun, let me ask maybe a provocative question. So you presented such a clear logic. Was there an opportunity for your community to predict that the measurement would have been made of the cosmological constant at anywhere near its value?
You mean in retrospect or when it actually happened?
Well, I mean, you're doing theoretical physics. You're doing theoretical physics, and, sometimes we can predict in advance of experiment.
Well, actually, we are beginning to see things like to say, yes, in this kind of thing, we should have expected the cosmic constant to be there, and so forth. So, for example, one of the Swampland predictions is that Minkowski space itself, flat space, is in the Swampland.
Okay, but
And so therefore, we would have said, so now that is one of the criteria. So yes, indeed, I don't believe flat space with no energy exists. So therefore, yes, I would have said, we would have, well, it's positive or negative, I'm not sure, but to say zero is a bit bizarre. In fact, if I were to guess, I would have said it's probably negative, because the negative ones are the ones which we can argue they're really stable and exist. But so if I were to bet back then, I would have probably bet on being negative.
Okay, then let me ask the harder question, because this one we'll be able to test. So experimentalists who do microwave background and other things are trying to measure whether there's any evidence that it's beyond a cosmological constant. And so far, it's been consistent with the cosmological constant. Do you have any ability to predict? I know you presented it roughly as two independent hypotheses.
Exactly.
But
so I think that's one of the areas we're still debating in the community as whether, so what Lars is referring to is whether or not we are in the situation at the bottom of this one, which is basically what we call dark energy with not much structure, or the thing which is rolling. The rolling one, if it really is rolling, we will find out, and as long as the slope is not too small, we will see some evidence of it if it's there. So, yeah, so indeed, that would be extremely interesting to think about. So we have models, and we have studied conditions where fit with the experimental data that we have today of the rolling possibility. So right now, I think that I'm not sure. We are not sure what it could be. I would say that the fact that in string theory we have difficulty constructing these, but not so much difficulty constructing these, might suggest this is the way to go. But it might be our inadequacy in construction of string theory. So we do not know the answer to that yet. It's a bit risky to predict that one.
Well, I just wanted to touch what you just said. Are we limited? Why are humans able to predict these things and Schrödinger's cat is not? I mean, is there a limit to what
human intelligence can perceive?
Well, I'm not as intelligent to be able to answer that question, unfortunately. But yeah, I don't know. I don't know whether there's a limit or not, but that's a good question. I think probably if the answer is known, our intelligence would not be able to decipher that.
Yes, you spoke of the majority of geometries don't lead to a viable solution, if I remember right. And then you spoke of these jewels that work out.
Yes.
There's something that bothered Feynman a lot, and that is of the 20-some-odd constants in physics, if you changed any of them a little bit,
yes.
we wouldn't be here.
Yes.
So that's like what we're in now is a jewel.
Yes, exactly. Now, so I'm convinced that we are in a very special situation, not only because, I mean, what you said is the manifestation perhaps of that. I do not have an understanding of why the values of the universe are the parameters that we have, which supports our life and so on and so forth, why they should be like this exactly. What I do know is that there are only finite number of possible universes. Finite is you cannot just adjust dial things, I like this, I know, they're finite numbers are fixed. So therefore there would be, by definition, some jewels. It's like, you know, you look at these polygons, symmetric polygons and so forth and so on, but then you have these platonic solids which are very special. So we are like those platonic solids, where just 2 or 3 or 4 or 5 of them, that's it. And then all these other ones are kind of not the relevant ones. So somehow they're special. Now, the answer to the question that you're asking, which is related to why the parameters in our universe are so fine-tuned for our existence, I mean, there's this principle, anthropic principle, that says, yeah, there are many universes, and one or the other, well, if there are a huge number of them, one or the other one has conditions more amenable to our existence, and therefore, yeah, so that we are fine-tuned because we are observing it. So it's not surprising. That would be an answer. I'm not sure if that's a good answer or not, but that's the what we call the anthropic principle. So yeah, so that's an answer. But the fact that we are in special situations, I think, is more theoretically based.
Okay. Thank you, Cumrun.
Thanks.